Well, let's start. And today I'm going to continue talk of Mikhail. And I would like to say how these Whittaker vectors and Whittaker functions can be connected with Hamiltonian reduction for classical Toda chain, and what is the general scheme. And I will use some written slides. Maybe it will be too fast, but you can stop in any moment. Well, and let's start from classical Hamiltonian reduction for Toda chain. And we should start with coadjoint bundle to LE group. And here G is a Lie group, small g it's Lie algebra, and G star is dual space. And here we have a symplectic form, and we can just think that this G is SLN, and here instead of these brackets, just trace of product of two matrices. Is it okay? I hope yes. Anyone?
Okay.
And for connected Lie group, we have Iwasawa decomposition. This group can be represented as a product of N, A, and K, where K is a maximal compact subgroup, A abelian, and N and plus idempotent, one of them. Here, and plus is defined as an idempotent subgroup with Lie algebra spent on all positive roots. Okay, and if our G is SLN, this N plus is upper triangular matrices with ones in any diagonal element, and A just diagonal matrix, and K maximal compact is SOM. And one general formula for Toda, that phase space of Toda chain and reduction we have to do for Toda chain. We should reduce using action of N plus and K, and it will be reduced phase space.
Maybe it's useful to mention that Iwasawa decomposition is just a kind of Gram-Schmidt orthogonalization.
For SLN, it's just orthogonalization, yes. And this N plus just Gram-Schmidt basis vectors, probably. I hope yes. And K is a matrix of shift, matrix of basis changes. Well, and let's describe the action.
No, K is from SON. So
yes, K is change of basis, and N plus is vector of basis vectors. 1, and the second one is 0, 1.
I think K consists of orthogonal vectors, and N plus.
Yes. Probably yes. Yeah.
It consists of Gram-Schmidt orthogonalization procedure, which makes orthogonal vectors step by step. Yes, so this is why it is triangular.
Yes. Well, and let's describe the action. We have action of n plus and k, and n plus acts by left multiplication and k acts by right multiplication, because both of them are subgroups in G. We can just multiply G by n and by k minus 1. And minus 1 here for in right action for homomorphism property, that if we consider two actions and their combination is just an action of k prime and k2 primes. Well, and we describe the action of n plus and k and j on G, and the general scheme in Hamiltonian reduction says that if we have an action on our base, then we can lift this action in a Hamiltonian way on the conjoint bundle, this one. And Hamiltonians of action is just a pairing between A or alpha canonical one form and Vxi, which is just a vector field which associated with this action. And the definition of Vxi is here. We should just use select a one parametric subgroup in n plus, which is generated by an element of n element of the algebra of n plus. And after that, just compute a angle vector. I hope this calculation is very simple, and we just get such vector fields. Is it okay?
Yes.
Almost yes.
And now I recall that alpha is a canonical one form. And we substitute these vector fields to alpha, and we get Hamiltonians for these two actions. And now in this moment we have two Hamiltonian actions from the left and from the right. Okay.
So, and eta, what is eta?
We live in our phase space is coadjoint bundle, which is trivial. And here we have G, and here we have eta.
Okay, yes.
Just a form on real algebra. Well, and for Hamiltonian reduction, we should choose a value in our we choose fixed value of a momentum map and factorize it by a stabilizer of its value. And let's now describe momentum maps in this scheme. And momentum map is a function from our phase space to a dual of the Lie algebra of our group acting, for example, here and plus and k. And this definition is written here, that if we pair our Lie algebra generators with momentum map, we should get our Hamiltonians, which are constructed using this Xi which is a generator of Lie algebra. And this is the definition of momentum map. And now we can calculate it. It is very simple because here the form of our Hamiltonian is now pairing as we want, and we should just choose a projection onto our dual to Lie algebras. Okay. Not. We define some function. For example, here we have minus eta paired with psi k, but this eta is from G star, but psi k is from k star, and only non-zero pairings will be if we just take a projection. I hope it is okay or not. Okay.
У меня сейчас висел интернет или у вас?
Не знаю.
У меня нормально.
Хорошо.
Well, and here, okay. Did you understand how I computed?
May you repeat, please?
In the previous slide, I have calculated this h psi k. And it was just minus eta psi k. And psi k is from что там?
Lie algebra.
K, which is a subset of G. But our eta is from dual to a whole algebra. But here, our momentum maps should maps to dual to subalgebra. And we should use here projection. Because if all parts in our eta not in K star do not impact this pairing. Okay.
Oh. Well, okay, it's clear. But if you don't take projection, you update the same.
Yes, but
Okay.
our momentum, I try to calculate this mu depending on G.
I'm
and
asking
theta.
because in the beginning I didn't understand your statement, and I had impression that otherwise, if we don't take projection, we obtain something wrong. No, okay, so I see.
Projection for computation, yeah.
Of course. So the result does not depend whether you take projection or not, but it's more convenient to take. Okay.
Because we, in our action, is not action of the whole group from the left and from the right. Because if we Hamiltonian reduction, our dimension of our phase space is dimension of the old phase space minus dimension of the group and stabilizer. And here we are trying to choose a large enough stabilizer and a large enough group. And to have our dimension of this minus 2 dimension of this. Well, and maybe after that it will be better to see. But now let's continue with momentum map. And we want to choose a value of our momentum. And the way is to choose 0 momentum for K action, and for N plus action, if we can use any, for SLN, for example, we can use any matrix with non-zero elements below the diagonal, but we fix momentum in such a way that we have non-zero elements only in the first diagonal below the diagonal, and all these elements are just ones. And we can choose, for example, different elements and nothing changes. But here we choose ones below the diagonal. And in this Lie algebraic notation, we just choose sum over all simple roots and take dual elements. And this, if we use trace to identify G and G star. Well, and this is lambda. And we defined this. And the next part, we have to calculate stabilizer of this value. Okay, and for K, we have just 0 momentum and the whole group stabilized. But for N plus, there is not so obvious that stabilizer of lambda N plus is also N plus. And how we can see it? And let's consider the left action. And we described it in this way. And to lift it to Hamiltonian action, we should act on our component in G star by coadjoint action. And now we want to calculate a stabilizer. What is a stabilizer? All n's, n, and for these n's, we want to not to change this momentum value. And it can be rewritten by this action on psi in n plus. And now let's use the form of our lambda n plus. It has non-zero elements only for simple roots. So the only non-zero pairings for psi is can be obtained only for parts of psi which correspond to simple roots. We have, for example, for SLN, we have in psi all elements here non-zero, but non-zero pairings with lambda only for elements above the diagonal. Okay.
Okay.
And now we want to say for which n, if we adjoint, if we act adjointly on psi, for which n we obtain the same. And the answer is for every n, because you can write this at n psi. It is psi plus some commutators. The leading order is psi, and all commutators. You cannot obtain elements above the diagonal using any commutator. You will obtain the second above and the third and all other elements. For example,
They don't correspond to simple roots, yes?
yes, which not only simple roots cannot be obtained using commutators, and therefore, for any n here, our leading order is psi, and only here we have simple roots, simple root parts, and then stabilizer is also n plus. Well, and now we have stabilizer here, of course, K, and our reduced phase space. Well, and how to describe this reduced phase space? And we have everything to do. Well, first of all, we can use our Iwasawa decomposition and use our stabilizer to put this G to a diagonal matrix U of Q. just because for every element of our Lie group, we can by left and right action just obtain a diagonal matrix. And after that, we will use these two conditions. Our eta is our projection of our eta on K star is 0. So our eta lies in the orthogonal space. And in minus alpha star, we have this space K star, and now we have eta in this space. And let's call elements in, let's choose a basis in this space, and for eta some coefficients. And here we write coefficients pi I, which cannot be fixed anymore. And here we have coefficients C alpha for any alpha, any root. And the last projection fix this C alphas. We calculate projection after the adjoint with a diagonal matrix and obtain just coefficients which is in Toda Lax. Only for simple roots, because our momentum is fixed be non-zero only for simple roots, then we have non-zero elements only for simple roots. And the values are just roots acting on our Q in Cartan. Okay. Anybody? Is anybody hearing?
Yes, yes, but a bit fast. I'm trying to understand.
Well, and let's go slower. Maybe some questions. Let's discuss.
Oh, well, okay, more or less clear. I cannot, at least I cannot formulate any reasonable question.
And maybe a question for me, and we obtain here eta. What is eta? Why is it good to get such C alphas?
Even
Why is
because it look like a tridiagonal matrix.
Yes.
Like we want to.
We have a tridiagonal matrix here, and maybe for SLN, could you say what is alpha Q?
So Toda's coordinates.
For simple roots, we have just
Exactly, yes.
yes, and we here obtain Toda Lax. And let's discuss maybe one more question. I have written my phase space and omega, a symplexic form. well, it was alpha. But now let's write, let's write omega. And what is omega after this reduction?
dpd alpha. Okay, so and q is oh, I confused. So alpha is difference of q.
Yes, yes.
Mhm.
Well, and then we have this M reduced and the standard Poisson brackets here. Well, and now how we can use it, for example, for solving Toda chain equations, equations of motion. Here we obtained that eta becomes Lax, and let's consider a free particle on a group with this Hamiltonian. Just eta, no g, and we can consider any trace of eta in the any power here. And we have simple equations of motion, and now we can solve it. But when we here this arrow is for Hamiltonian reduction, after this reduction we have simple phase space, the star of A, but non-trivial Hamiltonian. But equations of motion can be solved using these equations before the projection. And if we write higher powers, we will obtain higher Hamiltonians. And we had here that these traces commutes before the reduction according to Poisson brackets generated by omega. And after the reduction, our non-trivial Hamiltonians will commute with respect to omega reduced, which is just a standard Poisson bracket. And this is the way how we can obtain classical Toda chain. And now the aim is to say how it is connected with quantization. Well, maybe questions for classical part, because it really goes too fast.
And this you consider not SLN, but something else.
You will write it. You want to write here something more. Maybe in a more invariant way. Something like, and it will be in some way connected with that what Mikhail said in the previous time. Our Hamiltonians obtained from Casimir functions. And to get commuting Hamiltonians, we should use we should also identify J star with J using not trace but Cartan pairing, and after that we should write G invariant yes, G invariant polynomials in the inversion development. Casimir's just, and here is the second one for SLN. Here it's written something like EJI EIJ, sum over all I and all j. But for other groups, we should also choose a Casimir function. And after reduction, it the form of Hamiltonian is the same. Well.
Okay, well.
And let's go to a quantum side. And Mikhail said us that we have Whittaker vector, and definition was connected with our n plus. And in but I don't remember, he defines for algebra, but I will define for group elements. If we have a representation of group T and plus of the whole group, and we choose elements from n plus, these Whittaker vectors should be eigenvectors of this action. If we choose, for example, for SLN, our n, typical 1 on diagonal, 0 here, and some elements here. And our Whittaker vectors are eigenvectors of them. Well, and how it is connected with the previous definition, because any character is defined only by our values on simple roots, as for Mikhail said previous time, that for higher groups we define our Whittaker vectors by values mu1 up to mu rank. And here it is presented. Well, but we will use slightly a different picture. We will use not only Whittaker vector, but also a spherical vector. Which is eigenvector of any vector from our orthogonal group. For example, for SL2, for algebra, we will have this. And the difference is not so big, but it will correspond to our classical picture. Well, could you understand anything from this slide? Or not? Let's discuss.
No, for the moment, more or less, everything is clear.
We use Whittaker vectors, which were used by Mikhail, and use spherical vector. Well, and this Whittaker function, now we define it as a function on a group. Mikhail has a function of phi, but now we define it as function on a group, and use the decomposition to get rid of these factors and obtain function only on diagonal matrices. Probably about. You can write it in this way. This Whittaker function, they will function on group, but it appears that they are function on A, only on diagonal matrices.
And could you show once more definition of Whittaker vector? Ah, so that okay. I lost dependency on me. Okay, thank you.
Well, and here, well, and now in classical case, we had this Casimir's, but now instead of Casimir's, we use Laplace operators, which is invariant differential operators. How we can obtain it? Actually, Mikhail said us how, because in irreducible representation Casimir function x as a scalar, we have to insert it in our definition of Whittaker function and obtain an action. And if we compute the action, for example, of Casimir C2 in the general case for all functions, not for Whittaker functions, but for all functions on a group, we will obtain just Laplace operator. And before we have a free particle on a group, and now we have a free quantum particle on a group. But if we restrict our Laplace operator on Whittaker functions, we saw that we have seen that the result is quantum Toda Hamiltonian. Just because of our restriction. And it is the same picture if we consider, for example, a hydrogen atom, and we have a Laplace operator, which is a second derivative over x, y, and z, but we can rewrite it as an operator acting on r, theta, and phi. And here we obtain that our radial part is non-trivial. And this is the quantum Hamiltonian reduction over SO3 action. And in our Toda case, this is a quantum Hamiltonian reduction over n plus times k action. Well, is it okay or not? Because it was very fast, but this is the aim of the talk.
Maybe can you make some kind of summary?
The history with Whittaker vectors and Whittaker functions is actually a quantum Hamiltonian reduction for Toda chain. And we used previously just a second Casimir function, but we can use all Casimirs for obtaining commuting differential operators after the reduction. And they will be higher Toda Hamiltonians. And now we obtain, in such way, we can obtain a quantum integrable system. Well, and the aim was to say that the picture with Whittaker vectors is a Hamiltonian reduction. Okay or not?
Okay.
Maybe
I think
questions.
This is okay, but I have impression that somehow you use well, how to say, simplicity of Toda chain, I would say. Can you obtain this in this way something else?
Yes,
For example,
Gaden, for example, quantum.
Also
And
not.
in more complicated way.
What kind of quantization of Gaden model you obtain finally using this?
Let me
type
see
of method?
what limit what we can obtain. Here we have to use
The quantum Gaden model can be solved by beta ansatz, for example, approach. Can you explain somehow that the group theoretical approach which you use here can be applied to the Gaden model and somehow related to beta ansatz?
I think that for SL2,
not very easy.
for SL2 we obtain the same that beta ansatz can provide. But for SLN, I'm not sure that beta ansatz is simple.
By definition, it's not very simple.
But here, I suppose we have commuting Hamiltonians using this reduction, but we should use not Lie algebra, but affine Lie algebra probably. And everything is more complicated, but we obtain some commuting Hamiltonians, and for SL2 is the same that beta and ZD. But for SLN, I don't sure.
Mhm. I see.
Well,